to basically ask us questions, or rather ask Professor Kalam questions about anything that he'll go through in this webinar. But if you do not have that function, which is next to the chat box, you can always just use the chat box to put in your questions. And for today's webinar, we are going to have a certificate of attendance, as well as the copy of the slides and recording will be sent to you within the next 2 business days from today. So if it's not in your inbox for your emails, then please check the junk or the spam mail. And the certificate of attendance will be sent to you within 4 business days from today. There will be a link and QR code that I will present to you closer to the end of the webinar. And you will need to fill that in within 48 hours from today. So once you fill that in, it will ensure that we get the slides, the video recording, as well as the certificate of attendance to you. Okay, so please ensure that you do complete it within 48 hours after the presentation. And just a little bit about ECT and what makes this special. So we are in Engineering Specialists College, and we've got industry-driven programs with UK recognized education, which is all made possible by our lecturers and instructors who are specialists within the industry. And we also have a unique delivery model. So for today's event conduct, please can you not include your AI readers in this? And then if you could just follow my instructions so we can have a seamless presentation, that will be very much appreciated. And once again, thank you for joining us. Today's topic is mysteries. So the mysteries we're talking about will be the case of the transformer that hummed at midnight. And it's going to be presented by Professor Kalam. Professor Kalam, if you don't mind, you can
Yes.
take over.
Can I take control, please, if you don't mind?
Yeah, sure.
Right?
Sure. Go ahead.
I'm taking
Yes,
control.
sir. Okay, thank you.
Right. Thank you very much, Kumo, for that wonderful introduction to ECT. And it's now my turn to continue with the presentation. We lost about 2-3 minutes, and I'll try to make it up so that you're not disadvantaged by staying longer than what you're supposed to stay. This is a bit long topic, but I'll try to make it quick. I just want you to understand that the way I deliver a lecture is quite different than traditional lectures that you might have heard. I like to make more of a detective type, forensic type, that type of lecture, where you have to think substantially, even during and after the presentation. And I'll tell you what to do. This is a unique example, and what we are doing in these mysteries presentation is the real world style mystery. So it's not a Mickey Mouse thing. This is actually happening as of today, right? And what I'm trying to tell you and let you understand that you should now start behaving like a professional, experienced engineer. And you as a professional engineer should be able to cover any condition when there's uncertainty around you. So this is not a fault finding tutorial. This is about thinking. This is about thinking like a professional. So this is the thing. I don't know what happened, but every time the transformer used to hum at midnight. Why? That is the question. That is the presentation. Now, a bit about myself. If those of you don't know me, I am based in Melbourne, in Australia. Okay, I've got a number of positions and in various institutions in Australia and overseas, and I have my own consulting companies and other things. You'll be happy to know that I'm a British graduate too. I did my PhD from Bath in England, long time back, maybe before many of you were born also. And I did my master's from United States and my initial degree is from India. I've got professional membership of all the major institutions. This is the agenda of mine. I'll quickly skip through the agenda and come up with my objectives. What do I want to achieve today? I want that uh, I want you to understand. I don't want you to do any calculation. No calculation. No formulas. No mathematics. No using calculators. Nothing of that sort. I want you to think. I want you to behave as I told you, like professional engineers, and you are expected to handle ambiguity. And you will find many strange things happen. Many strange things happen, especially in engineering, okay, which sounds very strange. And normally we say if you ignore it, you don't see it, then it's not your problem. It's just like one of those funny bird that we have in Australia. What it does is that when someone chases it, it goes and digs itself in the sand and thinks that no one is seeing it, no one's going to hurt him or her. So we must be able to recognize non-obvious fault symptoms. Not every time there is a symptom which is obvious. So many things which you have learned up till now, if you have done your undergraduate, in particular in electrical engineering, you have heard that and heard from your lecturers, your teachers, your professors about things which is absolutely obvious. And everyone knows about it. You've got textbooks in it. What I'm going to talk about today, that which is not obvious. And I'm going to say, don't think from one professional point of view like electrical engineering. Think in terms of a college of equipments around. So think in terms of systems. And in this presentation, I've got interactions between harmonics, magnetics, and mechanics. And I want you to develop the professional diagnostic reasoning that will give you the solution to this problem, because you don't have this problem in a textbook. Now, my next thing is that mysteries. Why are we studying mysteries? And as I told you, it could be a very minor problem. The transformer humming in the midnight, very minor problem. You could have overlooked it. But you want to know why is that happening. And in real systems, there's no clean solution, my friend. And this is where engineers are called. And this is where engineers are called. Technicians can't do this, solve this problem. So I want you to behave like an engineer, where you're going to have a structured intuition. Coming back to my original thing that I was saying, you will not have this in any textbook. And in any case, industry has their own thing and they don't believe in textbook completely. Because there are a lot of things which are happening. In this particular instance, the transformer was humming distinctly at midnight. And it's nothing to do with engineering and such, but more to do with physics and environmental changes. And I want to give you the solution right in the beginning. It could be due to, in the midnight, the load is light. So the overvoltage of a light loaded system. So in this particular instance, at midnight, industrial and residential power consumption has gone down substantially. This reduction in the grid load causes the system voltage to rise. The higher voltage, the transformer core into magnetic saturation, escalating the intensity of the core magnetostriction, which is basically the microscopic expansion and contraction of the core steel. The transformer is made of number of laminated core. That is one reason. That means at the midnight, the load is light. Then I think it could be also due to harmonics. Or in the harmonics, you have seen a DC offset. Late night, the grid switching paired with highly non-linear residential electronic idling, that is, EV chargers, computers, introduction of DC offset and harmonic distortions occur. These elements skew the normal magnetic flux path, translating into a harsher, loud hum. That's my second reason. The third reason is during night time, there's an acoustic drop in the ambient noise. So during night hours, the midnight hours, daytime background noise is not there. You do not have any traffic. You do not have any commercial operation. All that shuts off. The transformer frequency, which is twice the grid frequency, which is 100 hertz in a 50 hertz system, or 120 hertz in an American system, which is 60 hertz, this easily bypasses the human auditory masking and stands out to nearby residents that they can hear that humming noise. So, what makes this mystery engineering? And this is because of the behavior which is intermittent. It's a time-dependent symptom. It has root cause which is not electrical. And the human assumptions which makes into reality. Fundamentally, whenever we talk about mysteries, it emerges when our mental model of the system is wrong, not when the equipment is necessarily faulty. Here, I will show to you there was nothing wrong with the transformer. But still, that noise was there. So, I've told you what makes the mystery, what defines the mystery. It's just symptoms. There's no alarm. It's intermittent. I told you in the very beginning. It's time-dependent behavior. And the data is conflicting. And there could be number of explanations. So most of the assumptions that I will be talking about, it will all fail. So let me try and introduce the case, my friend. Let me try and introduce this case. You have got a large oil-filled power transformer. This transformer is in continuous service. For this particular thing in the midnight, protection did not operate. But everyone was complaining that there was a loud humming noise coming from the transformer at midnight. So, if there was nothing wrong, my friends, okay, what is that? Every person, everyone who was involved, everyone around and surrounding, the techos, the people who were living in the neighborhood, everyone was saying that the transformer is humming in the midnight. However, I could not get anything from the SCADA. So I want to stress that technically there was nothing wrong. Okay? That's what, in the first place where I look at it, technically there was nothing wrong. So what I do, I look at the report. And before I start the report, I want to tell you that there is a time correlationship This is a great clue that I have got. I've told you midnight. Remember that. So there's a time-based behavior that should raise a flag in your system. Because electrical fault rarely follows the clock. Electrical fault does not follow the clock. Whereas this followed the clock. Only in the midnight it used to happen. So the noise was starting after midnight. It stayed over there for several hours. It stopped in early in the morning. In daytime, there was no abnormality. Oh my God, where are we? Daytime, there was no abnormality at all. I could not see any problem during daytime. Only between midnight and early hours in the morning, that humming noise was there. So if I just think a bit more, I just want to go a bit in the background. And I know you know this because every student of electrical engineering knows this. What is a transformer? Okay. Because uh, that if you, I mean, I don't know whether you've done any lab in your second year in undergraduate studies when we were studying transformers at that time, you would have found that there's a small noise, humming sound comes. But I'm not talking about that noise. Because this noise that I'm talking about is between midnight and early hours in the morning. So timing does matter. Remember that. And one of the things that I mentioned to you was magnetostriction. And this is the collapse and expansion of the cold steel, which is the lamination inside the transformer. And typically, for a 50 hertz system, it's at 100 hertz, twice. And it has nothing to do with the load. It is not time specific and it is constant. So, as we are all engineers, you are engineers, I am engineer. What is my initial reaction? What do I think? I always like to take the easy option. Man, this transformer is behaving like poor Kalam. It is aging. It's gone old. Use by date is over. Okay. The core is loose. Is it possible that the core is not tightened? Is it a manufacturing problem? Or whatever it is, it's harmless. These are some of the comfortable solutions or explanations that any engineer would give. And this is dangerous. These four conclusions that I've given are dangerous because we normally jump, first of all, to aging immediately because that's the easiest excuse. The transformer is aged, change the transformer. And this is low risk. But you find that when you put it back into the system, after a few days, again the humming sound starts. At this time, you can't see the transformer is old. You bought a brand new transformer. So, my friend, what I want to say, what is a normal transformer noise? And the word that I used was magnetostriction. This is basically a property of ferromagnetic material like iron, nickel, cobalt, and it changes the shape or dimension when it is subjected to magnetic field, where the internal magnetic domain reorients itself. This phenomena allows material to convert magnetic energy to mechanical energy, and therefore you have this expansion and contraction, expansion and contraction. This is responsible for the hum in the transformer, and this is widely used in sensors, actuators, and transducers. So therefore, that there is a this problem is definitely known. So it is caused by magnetic restriction. It is primarily load independent, nothing to do with the load. It's constant over time, and it's twice the frequency, system frequency. So someone might ask, why the symptoms didn't fit the theory? Because my evidence contradicts the theory. You have to just trust the evidence that I'm talking about. Noise is always time dependent. Okay? Load did not increase. I told you, temperature did not rise. There was no oil or gas anomalies, nothing of that sort. So what any engineer would suggest you to do is to do some diagnostic study. And after doing the diagnostic studies, this is where our greatest doubt comes in. Because I will do, if you ask any engineer, they will say, I do DGA, dissolved gas analysis. And many junior engineers who are starting fresh, they will get stuck in this. Because when the standard diagnostic says okay, the more it says okay, the more the mystery deepens. You look at the quality of the oil. Has the oil burned? No, it's acceptable. You look at the temperature of the winding, stable. You look at the load current, not changed. So all our diagnostic are failing. So now, my friends, the problem is that if nothing is broken, what has changed? Why this is happening? And this is where the difference of techos versus engineers come in. The technicians can do without giving the deep thought that an engineer can do. This is the subtle difference between an engineer and a techo. As an engineer, you want to expand the investigation scope. So this is where you will break the monopoly of discipline. So you're no longer going to look only in the electrical engineering aspect. And this is a key moment that I want you to think. Do not think in terms of component, think in terms of system. So you do step-by-step investigation. When your protection relay shows absolutely normal thermal and electrical parameters, but noise complaint persists, you must isolate the noise generation from the transmission. So you investigate. As I told you, you would do the DGA analysis, dissolved gas analysis. Look at the acoustic profile mapping. Look at the THD, total harmonic distortion, whether it has exceeded the 5% level. Look at the total harmonic distortion due to the voltage. When you look at the DC offset, look at the hardware placement, look at the correct parameter configuration, and look at data logging. So you're not only looking at the electrical behavior, you're looking at mechanical response, you're looking at magnetic forces, you look at the network configuration where you look at your hardware selections and placement, do all the analysis that is possible, look at the instrument transformers where you can look at the total harmonic distortion, look at the DC offset, do all your monitoring, like you can do all your power quality analysis, your SCADA system, look at the sampling rate, look at the aggregation interval, look at the harmonic spectrum, everything that you can think of. And you will find that whatever you do, whether it's a mechanical and structural thing, whether it's a dissolved gas analysis, it's all the same. It's all the same. And don't forget, you must always look at the environment also. What type of environment this transformer is subjected to. So, my friend, you've done everything, but you have not been able to still have any clue of why this is happening. And you find it's very easy for you to reconfigure a network, especially in night, because that is normally done because of efficiency or maintenance at that time. So look at off-peak switch operation. Look at the capacitor bank when that is switching in. That's where the harmonics come in. The inductor and capacitor in resonance. Look at the feeder configuration. Look at the voltage regulation. My friends, why does nighttime matter? Why does nighttime matter? Because the network switching is at nighttime, and nighttime you will find it is not equal to the low complexity. So nighttime there's darkness. What else can happen in nighttime? Capacitor bank can be energized. There could be load change because of the EV and the industry load system. The harmonic profile can shift. This can all happen in the nighttime, my friends. This can all happen in the nighttime. Therefore, I want to go a bit to harmonics. One of the problems we have with power system protection, and power system protection is my area of expertise, I have never been able to conquer harmonics. And you find every protection system that you have are blind to harmonics. Because harmonics dramatically change magnetic pole without increasing the RMS current. This is because of that third harmonic, the odd harmonic, whose frequency is 3 times that of fundamental frequency. That means 150 hertz. The transformer core is made of lamination. I told you the core laminations are there with insulation between the lamination with the harmonic stacked together with the bowl. When a transformer is energized at 50 hertz, the lamination moves to and fro and vibrates 50 times in 1 second. If a third harmonic is present, the transformer lamination will now vibrate 300 times rather than 50 times in a second. This rapid vibration per second causes the humming sound that you can hear. And this can be reduced if the laminations are bolted very strongly together, so you do not allow the vibration to happen. So, my friend, harmonics are normally due to nonlinear load, magnetic distortion increases, and it's not always visible in the RMS value. And this can excite your mechanical structure substantially. Now, if you look at the harmonics and transformer code, electrical distortion becomes a mechanical sound. The link between electrical behavior to mechanical sound, this is a classical interdisciplinary effect between the electrical and mechanical. So you have the flux waveform, which is distorted. You have the magnetorestriction increase. You have a vibration in the core, which is amplified, and you hear the audible noise. A bit on resonance. What is this resonance? My friend, many people think that resonance is a failure. My friend, resonance is not a failure, it's a physics. Okay? You do have capacitor bank. You add capacitor. In transformer, you have got inductor. There's an inductance and there's capacitance. At certain frequencies, amplified. Harmonics are magnified. Very simple. XR equal to XR. So, my friend, resonance is there. In the midnight, remember, don't forget the midnight. I keep on coming back to midnight. Till midnight, the transformer was behaving normally to any abnormal condition. Only when the capacitor bank was switched on at the midnight, this problem started. Your harmonics increased, your co-vibration increased, and you could hear that audible hum. Someone might ask me, Akhtar, why did the protection did not operate? What was wrong with that? I want to make it very clear to you. Protection detects damage, not discomfort. There was no damage done, just a humming sound. Protection system detects damage, not discomfort or any nuisance effect. This was basically a nuisance effect. There was no overcurrent. There was no thermal overload. There was no differential imbalance. There was no insulation stress detected. Why the hell should the bloody protection operate? Tell me. Why should it operate? Nothing was wrong. So you might ask this question. Why did people notice the noise? I told you, the techos noticed the noise, those in surrounding living area noticed the noise. Everyone noticed the noise at midnight and early in the morning. You were disturbed in their sleep. Okay. These are all the human perception that went to magnify or amplify the case for humming. And engineering problems often become visible through human experience. So there was reduced ambient noise at night. Human hearing becomes very sensitive because there's no cars and other noise that you hear during daytime. And it's a residential property, so everything was in proximity was residential, no industrial noise was there, and psychologically amplification was there. So, my friends, I want to verify my strategy. Because remember, when you've got a hypothesis, it has to be tested, not defended. If you are a good engineer, if you've got a hypothesis, you must confirm the hypothesis, not just tell good stories. So how do you verify it? You do measurements. Measure the harmonics. Look at the sequence of the switching. Look at the correlationship. Find where the temporary capacitor isolation is there and do the monitoring of acoustic. Now I want to confirm my root cause. Noise had something to do with capacitor switching. Noise was there because the harmonics level increased. Noise created conditions where the noise ceased when the configuration changed. The root cause is now confirmed. So now you've got the evidence. It is not just an opinion. You've got all the evidence that you wanted. So you want to make sure that you can implement these engineering solutions. Okay. And you must remember that when we are talking about good good engineering often saves money. And it does in a quiet manner. It doesn't do hoo-ha about it. So I'm trying to highlight the cost avoidance and asset life extension. So your asset life increases. That means you have saved money. So yeah, your switching time has been adjusted. Your harmonic filtering has been added. You've installed monitoring equipment, but you have not replaced the transformer. Mind you, the transformer is very expensive, my friend. These the first three items that I talked to you about, the switching, the filtering, the monitoring, they cost a fraction of what the cost of a transformer would be. So I have tried to avoid the cost and risk. And this is an excellent example of asset management. I did not replace any unnecessary assets. I did not replace a transformer. I did not have any outage. I did not have a blackout because of this harmonic, because of this humming noise. I did not disrupt the service. There was no discomfort to my customers. And the systems improved. So this is an asset management per excellence. So what are the key lessons that I have learned? And this is what I want to reinforce, the technical learning. It is not only your professional judgment, but this particular slide that I'm talking about now, it ties the technical learning to a professional judgment. So your symptoms that you thought in the early part of the presentation today can be misleading. Your equipment can be incorrect. They're innocent, my friend. It was the interaction of the system, mechanical and electrical, and the time pattern matters. It was in the midnight to early in the morning. Many engineers make this mistake, my friend. The mistakes which are made by many of us is cognitive. That means perceptive and rational, and they are not technical. So, my friend, we as engineers should take a humility approach. And because many of the experienced engineers also fall because of their ego, that they know everything. So remember, the symptoms that we had early, they were misleading. As I told you, okay, as I told you that uh, that oh gosh, as I told you right in the beginning, the systems can be misleading. The equipment was innocent. The system interaction dominated, and the time pattern mattered. Okay, and this is the engineering pitfall. And I told you that it's cognitive, that's perceptive and rational, and not technical. So component level tunnel vision should be out of our equation. Over reliance on alarms and sensors should not be there. Do not ignore soft evidence. Do not just rush, replace, replace, replace. So don't do that. And the most important thing, my friends, we must display skill as a professional engineer. And as a senior engineer, you should be thinking in terms of systems. You should have knowledge which is interdisciplinary, Always look for evidence-based reasoning and communicate with all stakeholders. Then I always like to discuss few things. I don't have too much time, but I just give you the answer to that. But I would like you to think of the answer that I've given you. What view do you, if any one of the 16 people that are attending today's presentation, what would you 16 people investigate for? If the protection data is normal, but complaints by the neighbors are still there, that a transformer is humming. So you have to reason it out. Remember, this is nothing to do with engineering. This is communication. And would you just replace the transformer? Or go to your management and say, let's replace this transformer. Replace this transformer means $40,000 gone. Replacing some of these transformers, which could be multi-million dollar worth of asset over a noise issue when the unit is functionally healthy, believe me, no management is going to buy that. If you want to change the transformer, if it's at all necessary, you have to put a structured cost benefit analysis. You have to look at the asset health certification, look at the capex, look at the utility mitigation, okay, and then you have to look at how the tap changer works, the no load tap changer versus the load tap changers work, and you know, sometimes it might be very easy for you, instead of getting your normal transformer, get a transformer which is made by Maddox. Maddox transformer is a transformer which is Maddox is the company which produces anti-vibration pads, the high density sound enclosures, so that the noise is below 10 to 15 decibels. And this Maddox transformer, you can get it for a fraction of cost rather than replacing the whole transformer. So my friends, so my friends, can a junior engineer solve this? Someone who has just graduated from one of these British universities or the European universities, can they solve this problem? I believe, myself being a British graduate, I can tell as a junior engineer, I could independently manage the data collection and structural verification, but I will not be able to solve this problem. This is where critical experience is necessary. That's why I said experience. To get experience, you need experience, my friend. Critical experience is needed. You will have to get experience in acoustic engineering, in power quality dynamics, and most probably a senior mentor can give you that experience where he or she can interpret the complex wave phenomena such as the acoustic standing wave or structural resonance matching the tank's natural frequency and to safely execute high voltage adjustment. So how would you proceed to improve detection? And this is an interesting question. You will look at basically from a reactive complaint driven stance to a protective mitigation integration. Look at the acoustic baseline, look at power quality alarms, look at predictive maintenance. And by adding all these things, you should be able to improve the detection. My friend, let us look at This is not the only example. You also have examples like resonance incident and false scripting. You might have example of harmonics induced say maloperation. You might see another example of cable sheet heating, where the cable failures are due to induce current. You might see high voltage DC current vibration, harmonic vibration. You might see this operation from CD saturation. All this can happen. So I just want to end my presentation by briefly telling you that there's no formulas. I did not use a single formula. I did not use any single formulas. I also told you I did not use only electrical engineering. I did not want that all problems you think in terms of electrically. Sometimes you have to think in terms of sound and think in terms of time. You can think in terms of. So in this presentation, I want you to understand that we had a transformer which was humming at midnight. And I told you right in the beginning, I gave you the solution. This was due to magnetose friction, where there's amplification and contraction of the lamination. Okay. And I told you at night time, the ambient noise reduces, making the normal 100 to 120 hertz vibration audible. And therefore, you must look at physical cause. Look at that midnight factor. I did tell you it happened only in the midnight to early in the morning. Look at the resonance and the looseness. I told you laminations are loose. And investigating techniques, I have told you. Sometimes not all faults are failures. Time patterns matter. Network behaviors matter. And investigation beats assumption. So, my friends, I can tell you that I have taken you from becoming a student engineer to a professional engineer. I want to tell you right now my reflection, and I want to be mentor for you by telling you not all textbook problems have answers. My friends, it is so interesting. In real life, you have got very good stories. You as engineer must learn to listen carefully, curiosity, the technical skill. My final thought of today's presentation is that my final thought is today's presentation. The system was speaking. The question was whether anyone was listening or not. With that, I have completed my presentation. Kumo, it's all yours now. I can tell you my next presentation for ECT is on 12th March when I'll be talking about paralleling generators when two perfect machines refuse to share the load. And following that, on 19th March, I have got a presentation where the Earth fault that didn't return to us. These are some of the presentations that I have coming in due course. Sorry, my dates were wrong. It's the end of the month, isn't it? March instead of March, I should have said in in September, end of September, the last Thursday of September. I'll be talking about talent generation or whatever it is. You will get that information in any case from Kumo or from ECT website. Thank you very much, and Kumo is all yours.
Thank you so much. And thank you to all our attendees for joining us today. And thank you, Professor Kalam, for giving us this insightful presentation. I'm sure our attendees enjoyed it and they've learned a thing or two. So we do have a few courses coming up. and those are our bachelors for September and next year February, and our master's programs for this year October and next year February. So as promised, this does have a QR code for the certificate of attendance, and I've already put the link that you see on the screen. I've put it in the chat box. Okay, Manuel, we'll get to your question just now. Let me just quickly give the relevant information, and then Professor Kalam will answer your question. Thank you. So this is a QR code for the certificate of attendance, but if you can't capture it, I have included the link in the chat box. And we do offer short courses that are provided through EIT, and these are 3-month non-accredited professional certificates of competency. These are basically for upskilling and professional development that you can use hand in hand with your other qualifications you've obtained. So for that, we do have a promotion running up until the end of November, and that will give you a discount for our professional certificates of competency. So that's just for our professional certificates. And then secondly, I would also like to give you guys a link for our upcoming events, and you can hear Professor Kalam in his other presentations that he will be hosting. And I have included the events link there so you can see the upcoming events and register for the ones that you are interested in. And alternatively, if you want to see anything from us, I have included our link for our website. And please, just a reminder, you've got 48 hours from now to complete that form for the certificate of attendance, the slides, as well as the video recording of this presentation. And now, Emmanuel, for your question, and I believe your question was, does the humming from the transformer be reduced from the density flux core?
Can I answer that, Kumo, if you don't mind? Emmanuel, that's
Go
a
ahead,
wonderful
sir.
question. Thank you very much for that question. And now I'll give you a very brief but very pertinent answer. The answer to your question is yes. Yes, it lowers the magnetic flux density in a transformer core. Therefore, it reduces the humming noise. No doubt about it. I have told you in the beginning, the flux density affects the noise because of magnetostriction. When I told you about expansion and contraction of the core, then I talked to you about if there was lower induction, that means your magnetic flux density increases, it compresses the steel, there's more intense vibrations, and therefore you hear louder sound. And it also depends on the design. You can operate the core at a conservative lower flux density, it decreases the level, this quietens the hum. Okay, the whole thing, if you want to consider a trade-off, you can think in terms of size and cost. If you can design a core from lower flux density, that will require more magnetic steel and larger physical dimensions, which increases the weight and the cost. Can you understand? That is detrimental to the very fundamental of buying a transformer. You do not want to spend everything on buying a transformer. You can make any possibilities, but remember, size will increase and cost is dramatically going to be exponential. I hope I've answered your question, Emmanuel. The next question is for you. Oh, sorry. No
Yes,
other question.
so they, yeah, Paul was asking about he can't get the QR code. Okay, I'll just bring it up again. But if it's not, if you're unable to capture it, please use the link. I'm going to put it back here again, and then you can just use that link to actually, because it works the same as a QR code. So you can go ahead and use the link. And if there are no more questions, then we can wrap it up. And thank you so much. And yes, thank you, Professor Kalam.
Goodbye,
We will see
and
you on
yep,
Thursday.
on last Thursday of next month. Thank you very much,
Hmm.
and all the best. And thank you very
Thank
much,
you.
Kumo, for an excellent emceeing today's presentation. And goodbye to all of you. Look forward to seeing you again. Bye bye.
Thank you. Bye.